Hey gang, we talked about over the week last week, me giving you a little bit of a review since we lost a day due to our diversity day. So let's start out by taking a look at the study guide and talking about what's fair game and what we really are eliminating for this test based upon what we covered. Now remember, these learning objectives that we cross out, we're going to focus on those next week before spring break. But anyways, here we go. You can cross out metallic bonds. We haven't had a chance to talk about that yet. And along with that, alloys and their characteristics. So far we've talked about electron configurations. That's really review for us. And noble gas configuration really helps us just understand valence electrons. Correct chemical formulas for ionic compounds, that's just review. Lewis dot structures, yes, that's fair game. Coordinate covalent bonding, we have not talked about that yet. So that's off our list. Bond dissociation energy, another thing that we can cross off our list. And final one, molecular orbitals and hybridization, which we'll touch on next week. So now what I think would be helpful is if we just kind of work our way through these briefly, and I highlight some things that I noticed, some common mistakes. And what I think I'm going to start with is not these first three learning objectives, because I think you guys have shown me that you know how to do noble gas configurations. You know how to determine ionic compounds. And Lewis dot structures, you showed that you were quite proficient. We had quite a few homework assignments. So my only recommendation to you would be to look at the assigned problems where I had you draw Lewis dot structures. So that includes work from activity 13, where you actually built the models, as well as the homework assignments that included tables on structure, number of bonds around central atoms, shapes, that sort of thing. Just remember one little thing about resonance. The idea of resonance just means that there are more than one possible Lewis dot structure. And the example that we went through in class was SO3, although there are many others. Carbonate, which was an example of an ion, where we can draw a Lewis dot structure for it with resonance. And there are others as well, but these are just a few that we actually talked about in class. Next piece is something that can sound kind of scary, but really it's something we've been seeing all along. And this is this idea of valence shell electron pair repulsion theory and how it influences molecular shape. I'm going to switch here to an app that lets me kind of show the models here. And just remember that lone pairs and bonding pairs are fundamentally composed of electrons. And those electrons are going to repel one another. They're going to repel one another, and that repulsion makes molecules have a particular molecular geometry. So for example, for hydrogen fluoride, there's only one bonding pair here, and there's no true central atom, and we would call that particular molecule linear. That's an example of a linear molecule. There's really no other option here when you just have two atoms. So let's look at some that have more than two. Another key one that we've talked about on quite a few occasions is water. Now what this model doesn't show us are the lone pairs. There would be a lone pair in this region and a lone pair in this region. Those lone pairs repel one another. Those lone pairs also repel these bonding pairs here. Because of that repulsion, water assumes this bent shape. So the reason why water is bent is primarily due, or solely due, to those repulsions between lone pairs and bonding pairs. The same thing holds true for ammonia. Ammonia would be trigonoplanar if it didn't have a lone pair. And again, this model does not show the lone pair, but it would be in this region here where my mouse is. Okay? Because of that lone pair, it pushes all of these hydrogen-nitrogen bonds down a bit. And that's where we get this shape, which we call trigonal pyramidal. Okay? Now we can look at something that is very similar structurally, but does not have that lone pair, and that's boron trihydride. Okay? And boron trifluoride is another one that we actually had as a homework problem. In this case, all of those atoms are in the same plane. So we call this particular shape trigonal planar. The final one that I expect you to know is one that is pretty common from activity 13, and this is tetrahedral. Again, this shape is the shape that it is because of, in this case, bonding pair repulsions. Okay? So we can use how many bonds and how many lone pairs are on the central atom to actually be able to determine the shape. If we have 4 bonding pairs and 0 lone pairs on the central, it will be tetrahedral. If we go back to ammonia, there are 3 bonding pairs and 1 lone pair, and that makes it trigonal pyramidal. If you have a unique situation like boring, where you have 3 bonding pairs and 0 lone pairs, it will assume a trigonal planar shape. And if you have something like water, where there's just 2 bonding pairs and 1 or more lone pairs, in water's case there are 2, it will form a bent or angular shape. Okay, so let's go back to our study guide real quick and see what we've talked about. So we talked just briefly about VSEPR. The next thing will be, and we talked a little bit about molecular shape. Let's focus now on polarity, because polarity is something that tends to be pretty tricky, because when we talk about polarity, we can talk about it in terms of a bond being polar, and we can also talk about it in terms of molecular polarity. It's important that you understand the difference. So let's go back to our model here. In the case of water, if we want to know bond polarity, all we have to do is look at electronegativities, and I can label them here in this model. And you'll notice that oxygen has an electronegativity value of 3.5. Hydrogen's is 2.1. There's a big difference there. And what that means is oxygen is just better at attracting hydrogen's electrons, and the electrons in that shared pair there between them. So that means when we start to look at this bond, there is something called a bond dipole, which we can just show like this. Now notice how the bond dipole always just points toward the more electronegative atom. That just means that when we look at where the electrons would be, more often than not, the electrons are going to be closer to the more electronegative element, oxygen in this case. And we can see that when we click on electron density. We see this big dark region near oxygen. That indicates that oxygen has a good capability of attracting electrons to it, much more so than hydrogen, and that leads these bonds to be what we would call polar covalent bonds. Now, the cutoffs that we talked about in class, remember, those are just guidelines. So, and the guidelines, in case you don't remember them, we always look at the difference in electronegativities. So in this case, we would say, well, it's going to be a purely covalent bond if the difference in electronegativities is relatively small. And by relatively small, we generally say the difference has to be 0.4 or less between them. And if it's more than 0.4, we say that the bond is polar covalent. And if it gets to be even greater than that, generally around 2 or approaching a difference of 2, I think in class we may have mentioned 1.7, it doesn't really matter, because when the bigger the difference, as you start to get closer and closer to a difference of 2, that bond becomes less and less like a covalent bond at all. It's pretty much like an ionic bond where electrons are actually transferred. Okay? So general guidelines, just remember, bond polarities can be determined using differences in electronegativities. Now, to actually get to the point where we look at a molecule being polar or not, we have to remember that a molecule's polarity is going to be based upon 2 fundamental things. The first is what type of bond exists in the molecule, and there may be more than one depending on the example. The second is the shape. Just the shape alone can also cause a molecule to be polar. So let's look at a couple examples. Here's hydrogen. Now hydrogen, if we show their electronegativities, both of them are 2.1, so we would predict that this bond is perfectly covalent, because they don't pull any harder on each other's electrons than the other hydrogen does. Okay, so a purely covalent bond. The next thing we have to think about is, well, is its shape asymmetrical or not? And in this case, any way you flip it, it's symmetrical. So just due to its shape, this molecule would not be polar at all. Okay, so we say that this molecule has covalent bonds and is nonpolar overall. Now that doesn't mean that linear molecules always have to be nonpolar. And a key example of that will be hydrofluoric acid, HF. In this case, there's a big difference in electronegativities between hydrogen and fluorine, almost a difference of 2. Okay, so this bond, if we look at its differences in electron density, near fluorine, it's very, very dark. And near hydrogen, very, very light, because fluorine is so electronegative. Now what that means is there is a polarity due to the different types of atoms that are bound. Even though the linear shape isn't by its very nature going to make a molecule polar, this molecule is polar because of the atoms that are attached to one another. And let's look at another example. Ammonia is another example here where we have bonds that are quite polar, and due to their shape make the molecule polar. And in this case, the thing that makes ammonia polar is that lone pair of electrons here, distorting these shapes. So we have a molecule that's going to be polar whenever we have something called a molecular dipole. And a molecular dipole just means that there's a region of the molecule that's more negative than the other. And we can see that in this case by clicking on the option, and this yellow arrow just points toward the region that's more negative. If we go and switch to water, we'll see that water is also a polar molecule, again, because of the types of bonds and because of the shape. So remember, when you're looking at any problem, you need to ask yourself, what kind of bonds are there? And does the shape of the molecule make the molecule polar or not? And we can take another example here of something that has polar bonds, but ends up being nonpolar by looking at boron trifluoride. Now let me clear this out here, make it a little easier for us. Okay. So if I go to boron trifluoride and we look at it, and we look at the atom electronegativities, we see there's a big difference. There's a big difference between boron and fluorine, okay, bordering on an ionic bond. Okay. So we know these bonds are all polar, but there's a unique thing about the shape. So we have polar bonds, but the shape of the molecule is symmetrical. Okay? This is a symmetrical molecule. And what that means is all of these fluorines are pulling. Notice how all of these arrows are pointing in the opposite direction of one another, pulling on boron the exact same strength in the opposite direction of one another. And that means overall, there's no net molecular dipole. And if we look at the electrostatic potential here, we see that the molecule overall is relatively nonpolar. Okay? If we contrast this to another molecule that would be bent or trigonal pyramidal in shape, like ammonia, we see a much stronger polarity when we get those atoms out of plane with one another. So take a look real quick. The only thing that's different here between ammonia and boron trifluoride is the shape. Okay? Polar bonds in both cases, but in this case, because of its shape, it's a much more polar molecule overall. And here I'll switch to boron trifluoride just to convince you. Okay? Look at how those colors just become more muted. It's much less polar as a result. So we would call this molecule nonpolar because it has no net molecular dipole. Okay? There you can see no net molecular dipole. Whereas if we switch to ammonia, there we've got a net molecular dipole. So we can use that molecular dipole as a way to help us understand when a molecule is going to be polar or not. Another thing that we can use to our advantage is the tetrahedral shape. Now if we look at something like methane, you might say, well, this looks symmetrical. And the bonds within it, they're actually quite covalent because the difference is very small between carbon and hydrogen. So you'd say, yeah, I think that this is a nonpolar molecule. Well, to check it out, we click on molecular dipole and notice that there is no net molecular dipole. That means the molecule is polar. Now, what's one thing you think we could change about this to make it polar? Well, hopefully you said you could change one of the hydrogens and make it more electronegative. So a different element, maybe like fluorine. If we do that, it's still tetrahedral. But now, whereas the three bonds here on the left are covalent, or very weakly polar covalent, this bond between carbon and fluorine is quite polar. That leads to a net molecular dipole towards fluorine, and that makes the molecule quite polar overall. Okay? So hopefully that is a good little review about how you can look at molecular shape and bond polarity to be able to determine if a molecule is polar or not overall. So let's take a quick look and see if we can go back to our notebook and see what we need to cover still. So we've talked about bond polarity. Boom, that's done. We've talked about the role of electronegativity. That's done. We've talked about molecular polarity. That's done. And molecular shape as well. The final thing we really need to talk about is our types of forces of attraction, intermolecular forces of attraction, often called van der Waals forces. Okay? And the kind we talked about in class were London dispersion forces, dipole-dipole forces, and hydrogen bonding. Now, a couple of key things to bear in mind. In terms of strength, if you have a intramolecular bond, that's a bond that holds atoms together in molecules. So that could be something like an ionic bond or a covalent bond or some flavor of that, a polar covalent bond. Those are all much, 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 much stronger than intermolecular forces. Sorry for my writing, but you can hear me at least, okay? Now, within this realm of intermolecular forces, or what we called in class IMFs, the strongest of those is going to be hydrogen bonding. And hydrogen bonding is much stronger than dipole-dipole, and that's significantly stronger than a London dispersion force. Key things to recall about hydrogen bonds. Hydrogen bonding is not really a bond, and that can be so misleading when you look at that word hydrogen bonding. It's a force of attraction, okay? So it's not as strong as these forces over here, ionic and covalent. But remember that the molecule must contain hydrogen and one of the most electronegative elements, nitrogen, oxygen, or fluorine. For a dipole-dipole force to attract, to be able to form, you have to have a permanent dipole. That means the molecule has to be polar. And for London dispersion, anything can form London dispersion forces. And that's because they form through the result of a temporary dipole. Okay? Remember, another key thing about London dispersion forces is they're extremely weak. They're weak because they're short-lived. Those temporary dipoles don't last for very long. Okay? So, I think that's about it. We've covered all of our bases in terms of the study guide here. And I think we've talked about all of these particular types that you're going to need to be concerned with. Now, if you want a little bit of advice, okay, you know that typically the critical thinking section on any assessment tends to be the most challenging. So the types of experiences that we've had recently should set the stage for the critical thinking section. So think about the paper chromatography activity that we did last week. And also think about the recent predictions that we made about those 6 solutes and how they interacted with different solvents, water or hexane. Those types of predictions where you have to apply bond polarity, molecular polarity, and shape in conjunction with intermolecular forces of attraction will likely play a role on the test on Monday. Hope this was helpful, you guys. Please have a good night, get some studying, but also don't forget to get some good rest. I'll see you in the morning.